Hello, my name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on carboxylic acids and derivatives and nitrogen compounds. Basically it's topic 18 and 19 kind of mashed together. Obviously this is for the CIE specification, so it's the Cambridge Internationals. So if you're studying the Cambridge Internationals syllabus, then this video is perfect for you. And obviously, as the name suggests, we're going to be looking at some carboxylic acids. We're going to be looking at derivatives of them, so for example esters, and look at some nitrogen mechanism or compounds that contain nitrogen in there as well. This is obviously just one part of the video. There are a full range of all the topics for CIE on Allery Chemistry YouTube channel. Please go and have a look. All I ask is you hit the subscribe button just to show your support, and that'll be absolutely brilliant. Also, these are a series of PowerPoint slides, and they're actually available to purchase if you want an electronic copy yourself. They're great value for money. If you click on the TES link in the description box below, that's the link where you can buy them from, then you'll be able to have a look at them there. I've kind of bundled all the organic year one stuff together, but I have bundled them further into full year one and year two kind of packages as well. So have a look in there. They're great value for money anyway. Okay, so let's have a look and see what we've got here. So we're going to start with obviously carboxylic acids. Now you'll probably find, and if you've watched my other videos, you'll hear this all the time, but it's just important just in case this is the first video you watch. All the CIE topics kind of overlap each other. There's a lot of kind of blending of some of the concepts into the individual topics, and particularly the nitrogen compounds one. There's a lot of kind of the stuff that you've seen before, so it just kind of repeats it or reinforces it, I suppose, is what CIE say. So so if I'll try and bridge them as much as you can, but if you haven't seen the previous videos, so 1 to 17 yet, it's a good idea to get a good kind of grounding of them first before you watch this video. But I will try and bridge as much of it as I can, just so you know where I'm referring to. Okay, so a carboxylic acid, they have the carboxyl functional group here, which is COOH. Functional group, looks like Q. Functional group it contains the carbonyl group, that's the C double bond O group, which we've seen before, and the hydroxyl group, which is OH. So it contains both groups, and obviously them topics were previous topics. So it's effectively, like I say, it's the mashing together of both of them. So carboxylic acids are named by finding the longest carbon chain and then adding oic acid at the end. Now the nomenclature of these, obviously we looked at the introduction to AS organic chemistry topic, which I think is topic 13. That obviously goes into the nomenclature a little bit more detail. Obviously this is just looking at carboxylic acids in particular. But effectively, they're relatively straightforward actually. When we're naming carboxylic acids, the carbon on the carboxyl group is always carbon 1. And the carboxyl group will always be at the end of a molecule because it's a carboxylic acid. So this one has obviously got 2 carbons, so it's ethanoic acid. This one is 4-chloro-3-hydroxybutanoic acid. You can see I've just tried to add some extra groups in there to kind of show you. And the last one is benzoic acid. Now if you're doing the full A level, you'll see benzene a little bit later on in the syllabus. Obviously we don't look at it in a great deal, but we don't look at it all really in year one. So but this is just an example of a benzene ring, so you've got this to look forward to in year 2. Okay, so how do you make carboxylic acids? So carboxylic acids can be made from nitriles, aldehydes and primary alcohols. So you've got various different methods of doing that. So let's look at primary alcohols and aldehydes first. And as you might have seen in the carbonyl chemistry topic, then you would have seen some of this already. So primary alcohols and aldehydes, they're oxidized to form carboxylic acids, and we use an oxidizing agent to do that. So normally it might be something like dichromates, for example, potassium dichromate, to do this. So there's your primary alcohol here. Primary alcohol oxidize to an aldehyde, and then that oxidizes again to a carboxylic acid, so using, say, dichromate. But they can also be made by the hydrolysis of nitriles as well, which you will have seen previously as well, but not this reaction. So there's your nitrile there. So nitriles have this CN group, C triple bond N group at the end there. Reacting it with water and some hydrochloric acid, an oxidizing agent, you form your carboxylic acid, and you form ammonium chloride as well, obviously with the nitrogen being kind of pulled off. So these reactions here are obviously methods in which you can make carboxylic acid. So fairly straightforward. Okay, and carboxylic acids, their kind of properties, they are weak acids, and they react with carbonates like other acids do to form carbon dioxide, and they react with bases to form salts. So let's have a look at some examples. Now, carboxylic acids, they are weak acids. Now, what that means is they dissociate partly. So they form some H plus ions and a carboxylate ion. But if you look at when we looked at equilibrium in a previous topic, then you'll notice that obviously strong acids dissociate fully and you produce loads of H plus ions. Carboxylic acids are an example of a weak acid, and equilibrium kind of lies towards the left rather than actually producing loads of H plus ions. So there's your equilibrium reaction there. So obviously equilibrium lies well to the left. You don't get many of these, and this is why carboxylic acids are actually classed as a weak acid. And obviously the whole family of carboxylic acids are. So as they're acids, they react with carbonates, as I mentioned before, and they form a salt, carbon dioxide, and water. So let's have a look. So this is just your classic acid acid-base reaction. But anything where you're reacting it with a carbonate, you will form carbon dioxide. So you can see here, you've got your carboxylic acid. So this is ethanoic acid. Reacting with sodium carbonate will form sodium ethanoate, which is this substance here, plus water and carbon dioxide. And obviously the reaction between ethanoic acid and sodium hydroxide, so this is sodium hydrogen carbonate, should I say, not sodium hydroxide, then obviously this will form sodium ethanoate, carbon dioxide and water in the same. It's just a different form of carbonate, that's all. And obviously acid-base reactions, they are very... excuse me, it's hay fever kicking in. So the reaction between an acid and a base, you've got your acid, carboxylic acid there, reacting with your base, and that will form your salt plus water, which is at the end there. So your salt will be sodium ethanoate. This is just the classic acid-base reaction as you would find anywhere else. Okay, so as they are acids, they also react with some metals as well. So, for example, we're going to look at magnesium here, and they will also react with ammonia to form ammonium salts too. So, let's have a look. So, here's the reaction between ethanoic acid and magnesium. So, you've got ethanoic acid, which is here, reacting with magnesium, and you form your salt. You form your salt, yes, this is your salt here, and you form hydrogen gas. So, like with a lot of metals reacting with acids, they will always produce hydrogen gas, and obviously the salt here as well. And the reaction between ethanoic acid and ammonia is here. So you've got ethanoic acid plus ammonia, and that will form your ammonium salt as well that's produced. So you'll always get this. Remember, when you react ammonia with an acid, you'll always just form a salt. You won't actually produce any water with it. Okay, so let's look at some derivatives of carboxylic acid. So a derivative is like a side branch, I suppose. So we can react alcohols with carboxylic acids. We can also react it with acid anhydrides as well, but you won't really see a lot of them. It's just an additional chemical. It's mainly the carboxylic acids that we're going to look at here, of course. And this can be used to make esters, and they have the COO group. And there's carbonyl groups that kind of flank the two ends of this functional group here. So an ester is produced when basically we react a carboxylic acid with an alcohol. And that's it. And we use a sulfuric acid catalyst. And you might have done this in the lab as well in beakers. It's quite a straightforward reaction, to be honest. So here's an example. Here's your carboxylic acid reacting with your alcohol with an acid catalyst. That'll form your ester, which looks like this, and water. And just to try and illustrate where the kind of components come from. So the blue is obviously the carboxylic acid. This is your alcohol. Now what happens is the OR bit from the alcohol basically swaps places with the OH bit on the carboxylic acid. So that's basically the difference there and how they're joined together. And then obviously you form water as well. So I find when you're looking at these types of reactions, that actually it makes it easier when you actually colour code the atoms and you can see what's going on. All right, okay, so carboxylic acids, they can be reduced to alcohols, and they can also be reacted to form acyl chlorides as well. So with acyl chlorides again, you'll see that more in year 2 chemistry rather than AS, but it's just kind of introducing it. So carboxylic acids, they can be reduced. However, they need a powerful reducing agent, and the reducing agent we normally use is something called lithium aluminium hydride, so LiAlH4, in a dry ether solvent. So that's the solvent that we use. So there's our carboxylic acid. We represent a reducing agent with 4 and a H, with a H in the square brackets. Obviously, you're going to need 4 of them, with some water, and then you produce your alcohol as well. Now, the reason why you need 4 of these is if you look at the number of hydrogens on this side, we've only got 4 of them on that side. On this side here, we've got 3, 4, 5, 6. We've got 6 hydrogens on this side here. So you're going to need a reasonable amount of hydrogens to actually make that work. Okay, so this is what you produce. So there's your ethanol there, your alcohol. Okay, and some of them obviously form to produce your water. Okay, ester hydrolysis. So esters can be hydrolyzed. Okay, so this means split using water. So hydrolysis, hydro meaning water, lysis meaning to break or to split. However, it can be sped up using an acid. So we call that acid hydrolysis instead, or base hydrolysis. So this is where we effectively break an ester apart to form its components. So let's look at acid hydrolysis first. So here, we're going to use a dilute acid to split an ester into a carboxylic acid and an alcohol. So, and we can use sulfuric acid or hydrochloric acid, and obviously the reaction is conducted under reflux for this. So let's have a look. We've got our ester here, and again, try to colour code it so you can see kind of the different components from it. Obviously, this is originally from the carboxylic acid. That bit is originally from the alcohol, and we're going to use an acid hydrolysis. There's your H plus ions. Now, what we form is your carboxylic acid, which is here. Obviously, the water. So with the water here, that will join to form the OH. And then obviously you form your alcohol here on the right hand side. So you can see here you've got ethanol. So the addition of more water, which is this bit here, will shift equilibrium to the right and we get more product that's formed. So generally you would add a reasonable amount of water into this and this should help push equilibrium to the right. And obviously you form the components that made up the ester in the first place, which is your carboxylic acid and your alcohol there on the right. Okay, let's look at base hydrolysis. So here we're going to use a dilute base instead to split the ester, and we're going to split that into a carboxylate ion and an alcohol. And obviously here we're using sodium hydroxide. We conduct the reaction under reflux, so that's obviously heating it up with your Liebig condenser vertically upwards. So there's your ester. And there is your hydroxide ion, that's your base, as you can see there. And obviously that will form your carboxylate ion here. And then obviously form your alcohol, which is there as well. So you can see all of this is balanced. And obviously we're splitting this ester into its components. So that's hydrolysis. Okay, so this is base hydrolysis. Okay, so esters are actually really useful. They're used commercially in industrial processes. So perfumes and food flavourings. So some esters have a sweet smell, such as pear drops, for example, and this makes them ideal in fragrances. You might have seen these before, like I say, you might have made them. They're used in solvents as well, so things like adhesives and glues, etc. And they have a low boiling point and they evaporate easily, and this obviously makes them really valuable in making glue. So obviously when you pour out a glue, or you put glue on say on a paper, then you expose it to the air, and that allows it to evaporate, and obviously that then leaves behind this hard resin, which obviously cements two components together. And they're also used in plasticizers as well. So they're used to make plastics a little bit more flexible. And you'll see later on in topic 20 when you look at polymerization. But they're basically used, or they can be used to allow a reaction to occur for polymers. The problem is they can leach out the plastic over time. So the plastic can become brittle over that period of time as well. So it's obviously not a... well, some plastics are more durable than others, but some of these plasticizers can leach out and can weaken the plastic. Okay, so we're going to look at some aliphatic amines, and we're going to look at seeing how you can make some of these. So aliphatic amines are made by reacting a halogenoalkane with excess ammonia. Now, a lot of these reactions you will have seen in previous topics. This kind of falls into the this falls into the nitrogen compounds topic. So this is topic 19. But a lot of these, I'm not sure why CIE have done this, but a lot of these are just recalling from previous topics. So it's nice to kind of summarize them, of course, but don't be kind of sitting there thinking, okay, I've seen these before, why is he doing this for? It's obviously all in the specification, so it is going to be quite important. So no harm going through it again anyway. So aliphatic amines are made by reacting a halogenoalkane with excess ammonia. So we can take a halogenoalkane, react it with excess ammonia, and we need to know the mechanism for these as well. Now here we're going to use a nucleophile, and this case we're going to use ammonia. So remember, a nucleophile has a lone pair of electrons attached to it on the nitrogen. This is going to go in and attack the delta positive carbon, and then it's going to kick off this chlorine there. Okay, so that's your nucleophile, and then obviously that kicks off the chlorine there. So we form an intermediate, as you can see here, and this is an alkyl ammonium salt that's been produced. It has a positive charge on the nitrogen, and we're left with this Cl- that's unceremoniously been kind of booted out of the original molecule, and now it's kind of floating around. Now the problem is this is not very stable, because this obviously got a positive charge here. That's got a negative charge, but it's floating around on its own. So this is where you need an extra ammonia molecule. And this is why we use excess ammonia, because you'll need 2 molecules of ammonia per molecule of halogenoalkane. So what I've done is I've taken the NH3 and I've split it up into the displayed formula, so you can see where the N plus is in the hydrogen. Now this time, this is actually going to act as a base this time. Okay, so the lone pair of electrons is going to go for this proton and take this proton, so it's going to be a proton acceptor, so it's a base, and then the electrons from this bond are then going to go in and neutralize that positive charge there, and that'll leave us with our NH2 group there. So let's have a look. There we are. And then we form our primary amine, and then what we have is our ammonium ion, because this will obviously form an ammonium ion, NH4+, will react with this Cl- that was kind of made homeless over here, and now they're joined together to form ammonium chloride, so you produce these 2 products. But the main product is this, so you form your primary amine, and obviously that's made by reaction with ammonia. Okay, so like I said before, 2 molecules of ammonia are required, and this is why the excess bit is so important. Okay, so let's have a look at reaction, so halogenoalkanes with the reaction of cyanide ions, again to make nitriles, so these are nitrogen compounds of course. So here we're going to use warm ethanolic potassium cyanide. That will obviously give us the source of cyanide ions, and we're going to carry this out under reflux. So very similar reaction. Here's your halogenoalkane. It's got this permanent dipole here, your delta positive, delta negative. Lone pair of electrons on the Cn minus ion, so the cyanide ion. This is going to act as a nucleophile. It's going to attack the delta positive carbon, and then it's going to kick off this chlorine here. There we are. Okay, so obviously this bond breaks. There we are. And obviously you form this. So you form your nitrile that's formed, and obviously you extend the carbon length now here. And then obviously you form your Cl minus, which is over here as well, your chloride ions. So the overall reaction here is obviously your halogenoalkane reacting with potassium cyanide, and that will form your nitrile plus your potassium halide. So obviously this bit here, this Cl minus, will react with the spectator ion of potassium, which will be knocking around as well. Okay, so potassium cyanide reacts with carbonyl compounds to form hydroxynitriles as well. So they were just nitriles that we'd seen before, but we can form hydroxynitriles. So the reaction occurs via nucleophilic addition this time, and it's obviously we use the nucleophile, which is the cyanide ion, so it's exactly the same. It attacks the carbonyl group, which is your C double bond O, and it adds on to make your hydroxynitrile. And a hydroxynitrile, as you probably guessed, contains a hydroxyl group, which is your OH group, and your nitrile group, which is the CN. So cyanide is used, or potassium cyanide, should I say, is used to produce the Cn minus ions in the first place. And what we do is we take potassium cyanide, dissolve it in an acidic solution, and then what that'll do is it'll provide us with our Cn minus ions in the first place. These Cn minus ions then act as a nucleophile. So remember, they go for the delta positive carbon. Make sure you show your polarities in the exam as well. That's going to be really important. But this goes in, attacks the delta positive carbon. This breaks and forms your, this breaks the double bond and forms a negative charge on the oxygen. And obviously we've got this intermediate here. Okay. HCN can be used as well. You don't need acid with HCN. It's just more difficult to use practically. So normally you'd use KCN to do that. It's just easier to handle. Okay, so let's finish off this mechanism. Oops. There we are. Okay, so then what you've got is this O minus, this intermediate, will react with the H plus ions that are in solution anyway because it's acidic. When we dissolve this in acidic solution, and it's the acid that will provide a source of H plus ions. So the lone pair of electrons on here, this is not very stable at all, so it's going to go straight for this H plus. Electrons move from here onto the H plus ion. Remember, the arrows show the direction of electron transfer, so it's going from this lone pair here to the H plus. And then this will form your hydroxynitrile, which is this product here. Okay. So the overall reaction, as you can see here, this is for your aldehyde, and this is for a ketone. So this reaction will occur for an aldehyde or a ketone. It doesn't really matter. The mechanism is the same. So the only difference is if we use an unsymmetrical ketone or an aldehyde, apart from methanol, then what we do is we get a mixture of enantiomers that's produced in this reaction. You would have seen enantiomers in a previous topic as well. Now enantiomers means that you'll have optical isomerism, and again you would have seen that in previous topics about what optical isomerism is. So I believe that would be in because this is to do with let me just check my notes. So you've got hydroxy compounds. I believe this optical isomerism is in hydroxy compounds in that topic, which is topic 16, but it's also in topic 13 as well, which is the introduction to AS organic chemistry, when we look at different types of isomerism and we talk about optical isomerism there. So just make sure you look back at them topics if you're ever unsure on anything like that. Okay, so that's it. That's everything you need to know for carboxylic acids, derivatives, and nitrogen compounds. Quite a few reactions there. To be honest, a lot of them are just overlapping from or some of them anyway, overlapping from previous topics. So there shouldn't be anything too new there, not too much anyway. Like I say, there's a full range of CIE videos on the Allery Chemistry YouTube channel. Please hit the subscribe button to show your support for this project. That'll be really, really good. Like I say, all these slides are available to purchase if you wish to do that. If you click on the link in the description box for the test shop, they will take them there. Great value for money and great to supplement your existing revision materials. But that's it. Hope that's helpful. Bye bye.